Welcome to this video, which covers the full solution to the practice questions from lesson 23, which covers the intersection of two planes. In the first question here, we are to determine the relationship between the following planes, and in both parts of the question, the planes are given to us in Cartesian form. So, to figure out the relationship, we are going to use matrices. We are going to put the two equation within an augmented matrix. So the coefficient of x for my first one is -1, y is 2, z is 3, and my constant is 12. So we get -1, 2, 3, and 12. And for the next one, we have 3, -6, -9, 3, -6, -9, and 2. The goal here is to reduce this value to 0. So let's try to see what operation we need to do in order to do that. So I'm going to keep the first one the same. And the second one, R2, is going to equal to, the lowest common multiple here is 3, so I would have to multiply this row by 3, that's 3R1. The next row doesn't need to be changed, or it just needs to be multiplied by 1. And in order to reduce this value to 0, I would have to add them. So let's put a plus sign in between, and let's use the values. So 3 times R1, it's going to be -3. 3 times 2 is 6. 3 times 3 is 9. 3 times 12 is 36. And I'm adding R2 here. So R2 is, for x is 3, for y is -6, for z is -9, and for our constant it is 2. Let's add all of them up. For x, -3 plus 3 is 0. For y, 6 plus -6 is 0. 9 plus -9 is 0. And 36 plus 2 is 38. Looking at our last row here, we can see that we get pretty much 0x plus 0y plus 0z is equal to 38, which is really impossible. We can't have any x, y, or z value that will satisfy that, and that would mean that our lines, or our planes here, sorry, are parallel. So we can say that the two planes are parallel and not intersecting, or just not coincident. Because if they were coincident, that would mean that this would also equal to 0, and that would mean 0 times any x value plus 0 times any y value plus 0 times any z value will equal to 0. And that would make sense because 0 times any value is 0, and if we add all those zeros up together, we would get 0. But in this case, we can't have that equal to 38, and therefore they're parallel and they're not touching, and therefore not coincident. And that is the final solution to our part A. Let's try part B of the question. We are going to use augmented matrix as we did before. And we have two rows. We got the first one, the coefficients of x, y, and z are 6, 8, and -3, and our constant is 9. And for our next one, coefficients of x is 10, y is 2, and z is 5, and our constant is -15. We need to find a lowest common multiple. First of all, I'm going to write the first one as is. And for the second one, the lowest common multiple here, we can divide them by 2 to get 3, multiply them by 10, 30. So 30 would be the lowest common multiple. You can use 60 and you will get the right answer. You just have like huge numbers. So you already will have very large numbers, but it'll be nicer to reduce them a little bit. So if the lowest common multiple is 30 between the first coefficients, then we can use 5 times row 1 and 3 times row 2. And in order to get a 0 here between these two coefficients, because they have opposite signs, we would have to add them. So I'm going to put a plus here. Once we have this, I am going to multiply row 1 coefficients and constant by 1. So 5 times 6 is 30, 5 times 8 is 40, 5 times negative 3 is negative 15, and 5 times 9 is 45. We are going to add 3 times R2, so 3 times R2, 3 times negative 10 is negative 30. 3 times 2 is 6, 3 times 5 is 15, and 3 times negative 45 is negative 45. 3 times negative 15 is negative 45. Okay, let's add them all up. 30 plus negative 30 is equal to 0. 40 plus 6 is 46. Negative 15 plus 15 is 0, and 45 minus 45 is 0. Okay, let's use our last row here to start our solution. So we have our augmented matrix in echelon form because we have the bottom left corner here as 0. And what we have here is 46 times y. Well, we have 0 times x, which is 0, plus 46 times y, plus 0 times z is equal to z. And equals to 0. So that just means that if we divide both sides by 46, we will get y is equal to 0. So that means y will always be equal to 0 when we are talking about the solution between these two planes. So what we're going to do now is we are going to plug that into our first equation, or the first row, and I'll write that here, or I'll highlight it. And we are going to have, I'll write everything down, 6 times x plus 8 times y minus 3 times z is equal to 9. 6x plus 8 times our y value, we found it to be 0, minus 3z is equal to 9. And then we will have 6x minus 3z is equal to 9. Note that for the parametric equation of the line, the format is x is equal to x naught plus bx plus t, y is equal to y naught plus by times t, and z is equal to z naught plus bz times t, where bx, by, and bz are the components of our direction vector, and this is our position vector for any point, and this is a position vector for some original or particular point. So our y value here is equal to 0 plus 0 times t, meaning that the direction vector will have a y component of 0, and the original point also has a y coordinates of 0. To find x and z, we basically have an equation that connects them, but we can go ahead and assign the t value to either x or z. It doesn't actually matter, and solve for the other one or isolate the other one. We often assign t to the last variable, so usually z and then y and then x. But again, just because I want to make sure that you know that it doesn't make a difference, I'm going to assign t to x for this one. And I'm going to rewrite the equation as 6 times t minus 3z is equal to 9. And I'm going to rearrange for z. I'm going to have it as 3z is equal to 6t minus 9. And what I've done here is I've added 3z to both sides to get positive 3z, and subtracted 9 from both sides to get 6t minus 9. And then I'm going to divide z by 3, or both sides of the equation by 3, and I will get 6 divided by 3 is 2, and 9 divided by 3 is 3. And that's my z value. And in this case, this is going to be my parametric equation. In my parametric equation, I'm going to have x is equal to t. That would simply mean that our original point here is going to be 0, or it's going to have an x coordinate of 0, plus 1 is going to be the x component of our direction vector multiplied by t. This should be multiplied. I don't know why I added that in, so I'm going to erase this. And then we are going to have y value is equal to 0. That means that here we will have the 0 as our component or component of the position vector of our original point plus 0 times t. That means the direction vector has a component of y which has a value of 0. And finally, for our z value or our z component, we are going to have 2t minus 3, meaning that our point, our particular point that we are choosing, will have a coordinate of negative 3 here, and we're adding that to 2 times t, meaning that the z component of our direction vector will have a component of 2. And this is one possible solution or one possible way of expressing the line, which is the intersection of the two plane, or which is the resultant of the intersection of the two planes. And I'm going to highlight this. Note that you could have also let t equal to z and then rearranged for x, and in that case you would get a solution which is slightly different in terms of the numbers, but it would still show the exact same line that is the result of the intersection of the two planes. And maybe I should also write that this is the planes intersect at this line, because we're asked to find the relationship and not just a parametric equation. So in this case, since we are getting a parametric equation, that is the line where the two planes intersect. In our last question, we're asked to determine the equation of the plane perpendicular to this plane over here. We know it's a plane because it has two direction vectors, and that it intersects it along this line over here. This is interesting because in the lesson we focus mostly on how to use augmented matrix to solve for line of intersection between two planes, but this is more of a conceptual question, and based on that concepts we can get to the final solution. So let's look at this. Let's draw this out to get an idea about what's happening. So we got a plane, and in this plane we will have one point. For sure, one of these points is going to be 1, 0, 1. And we are going to have two direction vectors that are showing the direction of the plane. So the direction vector, let's say one of them is going in this direction. Let's call that direction B. And let's say one of them is going in this direction. It doesn't really matter. We're just drawing the possible vectors here. So let's call this B and let's call this C. And now we're asked to find a plane that is perpendicular to this and that it intersects it along this line. And this line is going to have components 4, 3, 1. So for the line, I'll draw that using purple. It's going to have point 4, 3, 1. That's going to be on the plane. And let's say the line looks something like this. It doesn't really matter. And let's say this direction vector is 0, 1, 0. And let's call that the direction vector. Doesn't really matter. I'll just keep it at 0, 1, 0 there. And we want a plane, we want the equation of a plane that is perpendicular to this plane. So it's something like this. And that it is intersecting it at those points. So it will be a plane like this. So this plane and this plane are perpendicular and they are intersecting along this line over here. So we want the equation of this red plane, and for this red plane we need a point. When we have that point, we know that this line is part of this plane, so we have one point in the plane. I'm going to write that down. It's awesome that we have this. So 0.431 is on our plane. And we already have one of the direction vector as well, because we know this line is already on this plane, and we know its direction vector, and that direction vector is going to have, so direction vector 0, 1, 0 is going to be definitely on that plane. The only other thing that we will need is another direction vector on this plane. And we can find that because we know that this is perpendicular to this other plane, meaning that the cross product of B and C will give us this other perpendicular direction. So one of the direction vector on this is going to be this one, which is this, and the other one is going to be a line perpendicular to it, which is going to be perpendicular to B and C. So our other direction vector is, let's start giving some letters to this. So I'm going to call this one D, and I'm going to call this one E. So direction vector E is going to be the cross product of B and C. And once again, that is because this plane is perpendicular to this plane, and the direction vectors of the plane drawn in black is given as B and C. And if you want to find something perpendicular to those two, we need to find it using the cross product, giving us that direction vector E. Okay, to find the cross product, I'm going to use my ijk components of my unit vectors in the x, y, and z direction. For B, my vector is -1, 0, and 1, and for C it is 2, 2, 1. This is going to equal to I, and I am going to multiply 0 times 1 and subtract that by 2 times 1 minus j. And for j, I'm going to multiply -1 by 1 and subtract that by 2 times 1, which is 2, plus k. And for k, I'm going to multiply by -1 by 2, which is -2, and subtract that by 0 times 2, which is 0. And I will end up getting my components as -2 for x, -1 minus 2 is -3, times -1 is +3, and -2 minus 0 is -2. So this now means that I have the two direction vectors. I have E here, and this is my D. And if I want to write my plane, the one in red, we know that one of the points is going to be 4, 3, 1. So our plane equation in vector form is going to be R is equal to a point on that plane, 4, 3, 1, plus a parameter, let's use t, multiplied by one of our direction vectors. That's going to be 0, 1, 0. Again, that's this one over here. And we're going to add that to another parameter, lambda. Let's use that letter. And we're going to use this one, e, which we just found here, and that's going to equal to -2, 3, -2. One thing to notice in this question, in terms of the wording of the question, it's not the most clear one, actually. It says determine the equation of plane perpendicular, so this plane is definitely going to be perpendicular, and that this plane that we have is intersecting along this line that we've described. So that means that the plane that we have will definitely have this point and it will definitely have this direction vector. But that doesn't actually say that this line here is the intersection of these two planes. So keep that in mind for this question. So this line that we drew here doesn't necessarily have to be on the plane, the black plane over here, but the procedure for solving the question will involve this process because we need to find this plane which is perpendicular. If it's perpendicular, we have to use the cross product, and it intersects us along this line, which means that this line gives us the other, well, it gives us the point, or at least one point on the red plane and one direction vector in that plane, and we use that idea to solve it. And we are not asked in this particular question to have it written in Cartesian form or per metric form or vector form, so we can use whatever method we want to write our final solution, and that would be our final answer in this case. And if you want, I would encourage you to actually go and use these planes and vectors in the GeoGebra's calculator, 3D calculator online, and just look at the planes and where the intersections are and how they actually work. It's really nice to be able to visualize everything in 3 dimensions. And again, for some of us, it's going to be a lot more difficult to do this, and for some of us, it's going to be much easier. So with practice and practice, everybody will get much better at being able to visualize this in 3 dimensions. I hope that this video was helpful in giving you some practice in the intersection of two planes, and our last video, which is going to be the next one in terms of practice questions, for now is going to focus on the intersection of three planes. Thank you for watching.